Welcome back to the EE-371 video lecture. So in last lecture we have discussed the graphical method, that how to apply the graphical method or curvilinear square map method to estimate the capacitance between two conducting boundary. For that purpose we have selected um, an example in which the inner conductor was in square form and the outer conductor was in cylindrical form. This represents a coaxial capacitor. Then we divide the space between the inner conductor and outer conductor into 8 big symmetrical flux tubes, and then we further subdivide the one of uh, one of the big flux tube into sub flux tubes. So in this way you can fill the space between the conducting boundaries into a large number of curvilinear squares. This is known as curvilinear square map method. This is one method in which we fill one of the big flux tube into equipotential surface. Then we also draw uh, the flux tubes. You can also use another. You can draw the unit, the squares one by one. For example, draw one unit cell in this way, then but have equal size one by one, and in this way you can fill the big flux tube of this or the space in between two conducting boundaries into curvilinear square. You can either use this procedure in which we first draw the equipotential surface, or first draw the flux tube, then equipotential surface, and produce curvilinear squares in between the conducting boundary. Or you can draw individual curvilinear squares one by one. Fill the space between two conducting boundaries, uh, in between two conducting boundaries by curvilinear squares, but in one by one curvilinear square. And that way you can also achieve the mesh or grid in between two conducting boundaries. Then count the total number of the squares in between the conducting boundary, like this, and then along the boundary you can measure the total number of flux tubes. So then use these relation, you can define the you can define the capacitance, electric field, d field, surface charge density, etc. Take a drill problem. This problem is given on page 159 of the book, drill problem 6.4. In this problem we have given again a coaxial coaxial capacitor, such that the potential on inner conductor is 60 volt and the outer conductor is connected with zero potential. We have also given information about the equipotential surfaces, the with the constant potential difference of 20 volt, the space, the material in between two conducting boundaries, inner and outer conducting boundary is free space. The inner conducting boundary is very close to the left side of the outer conducting boundary, and on the right side, this is there is a large space in between the inner conductor and outer conductor. So in the remember that in this region we have weak electric fluxes, while in this region on the left side of the inner conductor we have strong flux fields, uh, and very close to the when the boundaries are very close, so in that case the fluxes are very strong, but when the boundaries are away from each other, then the fluxes are not so strong. So how to obtain the capacitance in between the inner conductor and outer conductor of this coaxial cable? We have also given information about these equipotential surfaces. So first, I told you in last example that first you will check the two-dimensional space of conducting boundaries for symmetrical flux tubes. So by checking this two-dimensional space in between the two conducting boundary, we can say that we can easily divide the space in between two conducting boundary into two symmetrical flux tubes, as I did in the lower figure. I have divided the flux, the space in between the conducting boundary into two symmetrical flux tubes. Then, as we have given information about the equipotential surface, so there is no need to draw again other equipotential surfaces. But if you want to include more equipotential surface, then that will increase the number of curvilinear square. So then you will get more accurate result, which we can obtain using the analytical relation. So then draw the flux tubes in the fill one of the big flux tube into a large number of subflux tubes. So in this case, I have filled the lower flux tubes into 19 flux tubes. As the big flux tubes are 2 in number, so multiply 19 by 2, we get the total number of flux tube in the space between the two conducting sheet equal to 38. And we have given information about the equipotential surfaces with the constant potential difference of 20 volt. So the squares in between the two conducting boundaries are 3 in number, that is 1 2 3, and the total number of flux in one big symmetrical flux tube is 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 18 19. So using this relation and the medium in between the conducting boundaries is free space, and using the free space permittivity we obtain the capacitance value, which is an approximate value. There you can obtain any value, but depends on your drawing, your skills, that how much you can obtain an accurate result. So in the I obtain the capacitance value equal to 112.2 picofarad per meter. Now we have asked to, this is capacitance per unit length. We have asked in part B of this problem, we have asked to find the electrostatic field at the left side of 60 volt conductor if its true radius is 2 millimeter. So you can do this in different ways. I did this, that is For instance, you consider three squares on the left side. As I told you that on the left side of the inner conductor, the fluxes are very strong because the inner conductor is very close to the outer conductor, so the flux strength is very strong. So on the left side, if I consider three unit cell of length one, each unit cell, let's say, has length 1 millimeter in normal direction, then in that case delta ln has 3 millimeter is equal to 3 millimeter, and the del V per 3 unit cells becomes 60 volt. So in for 3 squares we obtained 20 kilovolt per meter. For example, you want to want to find the electric field. Electric field is always in normal direction to the conducting boundary. So you can also use the first cell very close to the inner conductor. For example, in this, take the average value, or take for approximate value of delta Ln. Let's say that is 1 millimeter. So in this case, then you can obtain a result very close to the answer given in the book, which is 60 kilovolt per meter. Then we have asked to find the surface charge density at the left side of 60 volt conductor. So according to the boundary condition, at the perfect conductor, the electric flux density is discontinuous by surface charge density. Uh, Replace d by d electric flux density by epsilon naught times E, as the material in between the two conductor is free space. So rho s is equal to epsilon naught E, and we found this value on the left side of the inner conductor, that is in this region, very close to the inner conductor. The electric field value is 60 kilovolt per meter. So we obtain the surface charge density 531.27 nanocoulomb per square meter. So using this approximate method, graphical method, you can easily define the capacitance in between any two conducting boundaries of any shape. You can even include the non-linear effects at the which are producing at the edges corner of the conducting plates. So using this approximate method, we can easily define the capacitance between the conducting sheets, conducting boundaries. But remember, in applying this method, we ignore the variation in normal direction. For example, in this case, out of the screen into the screen, we ignore the variation in fluxes. But in electrostatic case, there exists no variation in fluxes along in a normal perpendicular parallel to the cylindrical structure. The flux is always directed in radial direction. So this was a little about curvilinear method, that how what is curvilinear square map method or graphical method, and how to apply this method to two-dimensional problems to obtain the value of capacitance, electric field, deep field, surface charge density, charge, etc. Now let us discuss that what is Poisson's and Laplace equations, and how to use these analytical or second order differential equations to obtain the to determine the capacitance in between uh, conducting plates. So we know that according to the differential form of Gauss's law, del dot D, that is divergence of D field, is equal to volume charge density. So, and we also know that D field is related to E with the help of permittivity of any dielectric material, insulating material. Let us call it equation number 2. We can also obtain the electrostatic field using the negative gradient of scalar potential function. So combine these three equations, we come across this equation, that is second order differential equation. Whenever there is a driving source on the right side of an equation, for instance this case we have driving source rho v, that is volume charge density. So this is called Poisson equation. Poisson equation. In for example, in some, for example, let us consider two conducting boundaries and assume that one conducting boundary is connected with high potential and and the second conducting boundary is connected with zero potential. As there is no source in between the two conducting boundaries, so then when we can remove the source factor in this relation. So in the absence of the source, this equation reduced to this form, del square v equal to 0. This is known as Laplace's equation, and del square uh, is known as the Laplacian operator, which can be expressed in rectangular coordinate system, that is del square v as a function of xyz equal to partial square by partial x square v plus partial square v divided by partial y square plus partial square v divided by partial z square equal to 0. This is the representation of del square v equal to 0 in rectangular coordinate system, or only del square v in rectangular coordinate. Similarly, you can expand del square v in cylindrical coordinate system, which is equal to 1 upon rho partial by partial rho times partial v by partial rho plus 1 upon rho square into partial square v by partial phi square and partial square v by partial z square. This is the representation of del square v in cylindrical coordinate system. You can also expand del square v in spherical coordinate system. So del square v in spherical coordinate system is equal to 1 upon r square times partial by partial r square partial v by partial r plus 1 upon r square sine theta into partial by partial theta into sine theta into partial by partial theta v plus 1 upon r square sine square theta into partial square v by partial phi square equal to 0. This is the representation of del square v equal to 0, or del square v in spherical coordinate system. Let us solve a numerical problem, drill problem 6.5 on page 162 of the book. In this problem, we have asked to calculate the numerical value for V in that is potential difference, volume charge density at point P in free space, F the potential function, that is potential difference, is in rectangular coordinate system, cylindrical coordinate system, and spherical coordinate system. So let us first consider the part A. In part A, we have asked to find the potential function value at this point. The coordinate of the points are 1, 2, 3. So replace y, z by and x by their corresponding values of the point given point in part A. We obtain 12 volt. So now we are going to define the calculate the volume charge density using Poisson equation. Uh, this one, how to obtain the volume charge density using Poisson equation. So expand del square v in rectangular coordinate system, and then apply each second order differential derivative along each axis to the potential function. First find the partial square by partial x square, then find partial square by partial y square, then find partial square by partial z square of the given potential function, which is equal to 4 times y times z divided by x square per plus 1. So differentiate the first term of this equation, um, which result in after mathematical manipulation we got the value of partial square by partial x square of the function equal to 32 times x square divided by x square plus 1 whole cube minus 8 divided by x square plus 1 whole square times yz. Uh, then on first different and then differentiate the second term with the second term of this equation, partial square by partial y square. So on the first differentiation you will get 4 times z divided by x square plus 1. On the second when you will apply partial by partial y per second time, so then you will have no variable, so that's why the value of partial square by partial y square equal to 0, because per second time differentiation of partial by partial y is constant, so the differentiation of constant is always 0. Then the procedure for this differentiation with respect to z is similar to the differentiation of the potential function with respect to y. So on first application of partial by partial z produce 4 times y divided by x square plus 1. On second application, partial by partial z become equal to 0. So we uh, we obtained only the analytical expression of partial square by partial x square, and the remaining two term in this equation are zeros. So this equation reduce to this form, plug in the values of x, y, z, and then simplify this and multiply the um, the whole factor by uh, the whole expression by with numerical value by epsilon naught. So we obtained the value of volume charge density, which is equal to minus 106.2 picocoulomb per cubic meter. This is cubic meter. Now let us consider the second part. In second part, we have given the potential function in cylindrical coordinate system at a point rho equal to 3, phi equal to pi by 3, z equal to 2. Now let us convert the as the angle is given in radian, first convert the angle into into degree. So 2 phi equal to 2 times pi by 3, which is equal to 120 degree. So at the given point in the problem, the potential comes out minus 22.5 volt. 22.5 volt. So we have obtained the potential which is equal to minus 22.5 volt. Now let us use the Poisson equation to obtain the numerical value of volume charge density, expand the del squared V into cylindrical coordinates, and then as the given potential function depends only on the value of radial axis and phi axis, there is no the given function doesn't depend on z axis, so the partial square by partial z square would equal to 0. First obtain the this the partial differentiation, find the analytical value for the first term in this equation, then find the analytical value of the second term in this relation, and as we have discussed that this part equal to 0 because the given potential function doesn't depend on the z axis. So apply when applying the first differentiation to the given potential, uh, we obtain 20 times cosine 2 phi, and by applying the second term in this equation to the given function potential function, we obtain the analytical value of the given function equal to minus 20 cosine 2 phi. So and partial square by partial z squared v equal to 0. So plug in the values of partial square by partial z square, partial square by partial phi square, and 1 upon r partial by partial rho times rho, and to partial v by partial rho in this equation, Poisson equation, and then simplify, we get 0 value of volume charge density. Then we in part C we have given potential function in spherical coordinate system. The coordinate of P point in spherical coordinate system, that is r equal to 1 upon 2, theta equal to 45 degree, phi equal to 60 degree. We have to calculate the potential at this point, and we have also to calculate the volume charge density at the given point in the problem. So plug in the value of r theta phi in this function, we obtain the potential at the given point equal to 4.0 volt. Using the Poisson equation and expand the Poisson equation in spherical coordinate system, then differentiate the given potential with respect to 1 upon r square partial by with respect to r, with respect to theta, and with respect to phi. So let us first differentiate the first the potential function first with respect to r. So in cylindrical spherical coordinate system, the second order differentiation is given by 1 upon r with respect to r is given by 1 upon r square partial by partial r into r square times partial v by partial r. So plug in the given potential, replace v by 2 cosine phi divided by r square. So the differentiation of the given function with respect to r produce 4 times cosine phi divided by r4. Now, as the given function contain no theta, that is the given potential function is independent of theta. So the differentiation with respect to theta of the given potential function produce zero value, as all other variable in this function are constant for partial by partial theta. So that's why the second term in this equation produce zero value. Uh, the third term now differentiate. Use the third term in this equation, which is the differentiation with respect to phi, 2 times differentiation with respect to phi of the given function. So that produce minus 2 times cosine phi divided by r4 sine square theta. So combine together all these terms, plug in all these terms in the Poisson equation. So we come across this equation. Plug in the value of phi and r in this relation and multiply the whole expression by epsilon naught. But the quantity inside the square bracket produce zero value, so that is why the volume charge density at the given point in spherical coordinate system is equal to 0. So this is how to use the Poisson equations to define the potential function, to obtain or determine the volume charge density, uh, and how to obtain. If you know the volume charge density, then how to obtain the potential function using Poisson equation. But uh, we will keep the Poisson equation to for only numerical analysis, not to define the analytical relation of volume charge density or potential function using Poisson equation. We will be using the Laplace equation to obtain the potential function and all other quantities. Now let us discuss the solution of Laplace equation, that how to apply the Poisson equation and where we can apply the Laplace equation to obtain the potential function. Once we get the potential function, then it is very easy to determine the electric field, D field, and the surface charge density, and from surface charge density we can easily determine the total number of charges reside on any conducting boundary. Once we get the charge distribution, then we can easily define the capacitance of their structure. So in order to learn about the application of Laplace equation, let us consider a parallel plate capacitor. That is the one plate of the capacitor is parallel plate capacitor is located at x equal to 0, having zero potential, and the second plate is located at x equal to d, having potential v naught. The material in between the two parallel plate conducting plate is some insulating material, and we have to define the potential. First we have to obtain the expression of potential using the Laplace equation. As there exists no source, so del square v equal to 0. This is known as Laplace equation, and the variation in the equipotential surface is along x-axis. So this means that the required potential function is a function of x-axis. Expand the Laplace equation in a rectangular coordinate system. In rectangular coordinate system, the Laplacian operator is equal to partial square by partial x square plus partial square by partial y square plus partial square by partial z square. As there is no variation in potential function along y-axis and z-axis, so these two variations are zeros in this structure, in the given structure. But there does exist variation along x-axis, so that is why partial by partial x is not equal to 0. So the Laplacian operator then becomes equal to partial square by partial x square, and the potential function only depends on the x-axis, so we can replace the partial square by partial x by total differentiation d square by dx square into potential function, so this whole thing equal to 0. Now how to obtain the expression for the potential function? So that we can do very simply by applying the integration. So on first integration, this equation reduced to this form, that is del v divided by dx equal to a some constant. Then again apply integration on both sides, which produce this potential function, that is v as a function of x equal to a times x plus b, where a and b are unknown variables. These are the constant of integrations. We will obtain the value of these unknown coefficient using the initial boundary condition, that is x equal to 0. At x equal to 0 the potential is 0, and at x equal to d the potential is v naught. So using these boundary condition, now we are going to define the values of a and b, and to define the final expression for this structure. So at x equal to 0 and v equal to 0, the given function, the obtained function produce b equal to 0, but a is not equal to 0. So the resultant potential function reduced to this equation, that is v as a function of x equal to a times x. Then apply the second boundary condition to define the value of a, which is unknown coefficient. So at x equal to d the potential is v naught. So using these condition in this equation, we obtained the value of a, which is v naught divided by d. So plug in the value of a in this equation. We obtain the potential function in between two conducting boundary, one which is located at x equal to 0 and the other which is located at x equal to d. So look at this this expression, this potential function. Basically now we will check this expression for the boundary condition, whether this function um, just satisfy the given initial boundary condition or not. So as we know that at x equal to 0 the potential is 0, at x equal to d the potential is v naught. So this function satisfy the boundary condition. So now from this function, now we can easily obtain the electric field using the negative gradient of scalar potential. And let us assume that the dielectric and insulating material in between the two conducting plate is some dielectric material having a permittivity epsilon. So we can also obtain d field using the expression of E field. Is the normal boundary as the normal component of D field, as we know that the conducting sheet behave like equipotential surfaces. So, for instance, the the plate located at x equal to 0 uh, um, is at this is at zero potential. So the surface charge density is what that is negative. And x equal to d, the surface charge density is positive. So the d field is directed toward negative x-axis. So d in this case dn an. So we can also write this expression in this form, where a sub n unit vector represent unit normal, and in this problem the unit normal to the conducting sheet is ax unit vector. So the dn component of d field is minus epsilon v naught divided by d. So according to the normal boundary condition, the normal component of D field at the conducting plates are discontinuous by surface charge density. So the magnitude of rho is become equal to epsilon naught, epsilon times V naught divided by D. That is Coulomb per square meter. Now the in order to find the total charge accumulated on one of the conducting plate, either on this or that. So uh, first, as in electromagnetic field theory, we consider a geometry that occupies the whole universe. So in order to define any specific behavior, we divide that structure into incremental parts, and then we define the that specific behavior for a single incremental part, and then we claim that that behavior exists toward the whole surface. So now divide these two plates into incremental surfaces. For an incremental surface of the two conducting sheet, we can obtain the total charge reside on that incremental surface, which result in q equal to epsilon time v naught into s divided by d. Now divide the charge, the obtained charge by potential. So this define the capacitance. So now you have learned that how to use the Laplace equation to define the capacitance in between conducting boundaries. So again we get the same result as we have used the boundary condition in last lectures for parallel plate capacitor. Now let us consider another geometry in which we have a conical conducting sheet above a planar conducting sheet. In between the conical shape conductor and the conducting sheet there is a small gap where we have a capacitive effect. So how to obtain this capacitive, how to define the capacitance in between the at this gap between the conical structure and the planar conducting sheet. So for this purpose, we use the Laplace equation del squared v equal to 0. So look at the figure. In figure, uh, it is mentioned that at theta equal to pi by 2, the potential function on this conducting sheet is 0, and at theta equal to alpha, the potential is maximum on the conical shape, on the cone surface. The conical surface, the potential is maximum, which is at theta equal to alpha, and at theta equal to pi by 2. But remember, this alpha is less than pi by 2. So the variation in the conical surface is with respect to theta. We have in this example we have given that the variation in surface occur with respect to theta. So this means that the resultant potential function is a function of theta only. The resultant function doesn't depends on phi variation, doesn't depends on radial variation. So del squared v equal to 0, and as I told you that how to expand del square v in spherical coordinate system. So let me to show you again using this one, as the variation in this example is with respect to theta, so we will be considering this one, this term of the del square v, which is equal to 1 upon r square sine theta times partial by partial theta times sine theta partial v by partial theta. So del square v equal to 0, we only consider the second term of del square v, which is 1 upon r square sine theta partial by partial theta into sine theta partial v by partial theta equal to 0. If you look at this term 1 upon r square sine theta, so for r equal to 0 and theta equal to 0, this produce undefined value. So eliminate this factor, uh, remove this part, this factor from this differential equation. So we left this one, as the given resultant function depends only on theta, so we can replace partial by partial theta by d theta. So after removing 1 upon r square sine theta, we come across this equation. Now integrate uh, this equation on both sides with respect to theta. So we obtain the above expression reduced to this form. Rearrange this one, so we get dv theta by d theta equal to a divided by sine theta. Again apply integration on both sides, and we know that the derivative of ln tangent theta by 2 equal to 1 upon sine theta. So we can replace the integration. If you integrate this formula with respect to theta, so you will get ln tangent theta divided by 2 equal to integration of 1 upon sine theta with respect to theta. That is ln tangent theta is equal to integration of 1 upon sine theta with respect to theta. So the this relation after second integration take this form, that is v as a function of theta, that is potential function, as a function of theta equal to a times ln tangent theta by 2 plus b, where a and b are unknown coefficient, and we will define these unknown coefficient and using the initial boundary condition, which are theta equal to, at theta equal to pi by 2 the potential is 0, and at theta equal to alpha the potential is v naught. So first apply the initial boundary condition at theta equal to pi by 2, where the potential is 0. So this condition produce b equal to 0. So the resultant potential function reduced to this form. Now we are going to define the value of a. For this purpose, we are going to apply the second boundary condition, that is at theta equal to alpha, the potential is v naught. So v naught equal to A times ln tangent alpha by 2. So the value of A becomes equal to V naught divided by ln tangent alpha by 2. So replace this A by this expression. So the resultant potential in between the conical surface and the conducting sheet becomes equal to this one. That is potential function equal to V naught ln tangent theta by 2 divided by ln tangent alpha by 2. Now we have obtained the potential function using the given information in between the conical surface and the conducting sheet. Now we can easily obtain the electric field using the negative gradient of scalar potential. So expand the nebula operator in spherical coordinate system and then differentiate the given function with respect to theta, with respect to phi, with respect to r. But in this case, the obtained potential function is independent of r and independent of phi. So we can only differentiate this function with respect to theta. So after differentiating the potential function with respect to theta, we come across this relation, that is E equal to minus V naught divided by r sine theta ln tangent alpha by 2 a theta unit vector. From this resultant electric field, we can easily obtain the relation for electric flux density. Let us suppose that the two structures, the conducting sheet and conical surfaces, are embedded in some insulating material. Then at theta equal to alpha, the at the conducting surface, conical surface at theta equal to alpha, we can now define the surface charge density. According to the normal boundary condition at the conducting surface, the rho is the d field is discontinuous by surface charge density. So using that boundary condition, we obtain rho is equal to minus v naught epsilon r sine alpha ln tangent alpha by 2. Now in order to obtain the total charge uh, reside on the conical surface, we have to integrate this surface charge density with respect to theta. With respect to surface, that is in the direction of theta, which is the incremental surface in theta direction is equal to r sine theta d phi dr, and the range for r parameter radial axis is from 0 to infinity, and for phi axis, that is phi actually vary from 0 to 2 pi. So the total charge for an infinite conical surface becomes equal to this much. For finite length conical surface, let's say r equal to 1, then the total charge distribution approximately equal to V naught epsilon times 2 pi r1 divided by ln. Bring the negative sign inside the argument of logarithmic function. So we can easily obtain the total charge reside on the or carrying by the conical surface, which is equal to V naught times epsilon 2 pi r1 ln. The inverse of tangent function is cotangent, this becomes equal to cotangent alpha by 2. So now we can easily obtain the capacitance C equal to Q V naught Q divided by V naught. So by putting the value of Q in this relation, we obtain the capacitance in between at the gap between the conical surface and the conducting sheet. and that is equal to 2 pi epsilon r1 ln cotangent alpha by 2. That's all. I think there in the book you can find more examples, and I also think that now you will have learned that how to use the Laplace equation to obtain the potential function in between the conducting boundary, and then how to use that potential function to obtain the electric field D field, how to define the surface charge density over any conducting surface, and then how to obtain the total charge carrying by that conducting surface. Once you get the charge distribution on any conducting sheet, then you can easily obtain the determine the capacitance between two conducting boundaries. Thank you.